Yes, unfortunately James was supposed to present this, but in his absence Stephen and I have been substituted in to speak about this very briefly, because the following two lectures I think are what should dominate this session and will. You've seen all of these guys already. This morning we learned about the opportunity around macular pigment augmentation for patients with AMD, and we'll learn more later on when we listen about the AREDS2 results. But there's been a lot of work, and as Randy Hammond has been saying time and time, that there's been a lot of work done in this and discussions and publications on visual function dating back many years. So the conversation around macular pigment and why it's important is not just for AMD. Visual function is one of the discussions. And the idea, of course, is not just about preventing central vision loss, but it's can you take this type of vision and create this better visual experience, this visual performance and comfort. And the implications of this, and we've heard, this was presented 2 years ago brilliantly by Professor Hammond. The implications of this are for sports people, drivers, people that use their vision every day, which is essentially everybody, but for fine detailed vision, shooting, for example. And there's a landmark paper by Professor Hammond that looks at this and its link and importance for baseball players. And why would it be? Essentially, for me, one of the reasons is the unique optical filtration offered by macular pigment and in the ideal location to do so. There's other reasons why macular pigment may enhance visual function, but I think primarily the ability of this yellow filter to remove blue light from the central portion of the retina. At the foveola, we know that there's no blue cones. So blue light is problematic, in short, for vision, and I know Stephen's going to touch on that in a little more detail. The sky is blue because of light scatter, short wavelength blue light. It's scattered before it gets to the eye. It's scattered by all the particles in the ozone, etc. And this light scattering before the eye, and indeed as it moves into the eye, cataract causes scatter, and optical media within the eye can further induce that scatter, and the effect of that is this luminance over the macula and low quality visual function as a result. So the theory is if you can optimize filtration in this specialized part of the retina, that you can impact on visual function in a very real way. And this is an example that was used by Professor Hammond in his last lecture. Disability, glare discomfort, all these parameters of visual function, which are important. And by the way, these are the same parameters that get worse and worse in patients with AMD. What this ugly-looking slide was supposed to summarize was, since Randy's Hammond 2 years ago, I had a quick look to see what has happened in the literature. And it's remarkable to see that in that short pace of time, there's actually 9 publications, a lot of them from Randy's group, of course, looking at visual function, supplementation with lutein, and its effect on visual function. And the quick summary of all these publications is that there appears to be a beneficial effect around supplementation with the macular carotenoids in the young normal person. So remember, again, this is not the person with macular degeneration. These are people without such retinal pathology. Very, very quickly, Stephen asked me to kind of summarize some of the response studies that lead up to the study that Stephen will present, and that is, if we take carotenoids, if we take lutein, if we take mesozeaxanthin, do we respond to them? And we started looking at this back in 2006 in Waterford. The first thing we looked at was safety, and the safety analysis is ongoing and it needs to be continued. But there's now 3-year data showing that none of the clinical pathology parameters assessed had any contraindications or safety issues associated with them. The very first study we did that included the 3 carotenoids was an exploratory study, and the first research question there was, if you take these supplements, does it get into the blood, does it have a real effect? And we see typical serum response here that you would expect. But what was unique, I think, about this paper, albeit in small numbers, was that we started to see changes in the macula, in the macular pigment, much, much quicker than we had seen with, for example, a lutein-only supplement. So this was interesting, and particularly the location of augmentation, so at that very central point that we measured at. We'll see from, or you've seen from some of Katie Marr's work, the different responses that you see in serum, but the quick answer again is that if you take these, you can get them into your blood in a very real and meaningful way. And this is published in the British Journal of Nutrition. and also interesting correlations then that you can see between the carotenoids, how they increase in serum, and how that affects macular pigment levels. This was one of my first papers. It was a study of over 800 people in Ireland, normal people without ocular pathology, and the conclusion from this work was that the main risk factors for age-related macular degeneration were associated with an independent lack of macular pigment, and Julie touched on that very nicely yesterday, how there continues to be this affiliation and association between these risk factors in large epidemiological studies and macular pigment levels, and this was one of the first findings that we had. What we noticed then in a subsequent paper was that the same risk factors actually had a link with the profiles that we were seeing in macular pigment. And Dr. Howard was discussing this morning the central dip, the atypical profile. And you know, when we start seeing these in smaller studies, the initial reaction was that it may be just measurement artifact, it may not be real. And we worked on that. We did repeated studies, and we saw that these were real artifacts, or real, rather, profile changes. And I know Toss Bernshot has published the ring-like structure as well, which introduced that when you measure it with the autofluorescence technique. What we know about these atypical profiles, as we've termed them, is that they are more common in people with those increased risk factors for age-related macular degeneration. And the idea here is that the dips, particularly the central dip type profile that you see, may be linked to a lack of a particular carotenoid mesozeaxanthin in that central part, given the studies that we've seen on the distribution of the carotenoids. So if you accept that a dip exists, and we've measured it, we've shown it's reproducible, it's there, the question is, can you modify that with supplementation? And this was one of the supplementation studies that we did to test that, and we've been talking about these three formulations a lot over the last 2 days. They're the formulations that we've been using. This was a study where we supplemented with these three. We essentially, from the 800 study, where we saw these dips in about 12% of the population, we invited them back and they were put on one of these three interventions. Here's the quick results. In the high lutein group, the profile pretty much didn't change over the period of supplementation. There was nothing more than measurement noise that we saw there along that spatial profile. That's kind of consistent with all the lutein studies that we've done. We've seen that it takes a long time, and Stephen showed it this morning in his presentation. Even in the AMD patient, you can see it can take sometimes 12 and even longer to get that response in the macula. The high mesozeaxanthin group showed a very dramatic augmentation in the very center of this, and again, this is not, I suppose it's not too surprising to see that given the location of the mesozeaxanthin in macular pigment. But then what we see is when you use all those three carotenoids, we've looked at it in terms of bioavailability, how does it get to the blood? The answer is yes, and now you can see that it has this enrichment of pigment across the spatial profile. So you get this augmentation centrally, but also across. So I suppose the point here is that if the objective of the exercise is to increase macular pigment, we think we're figuring out a way that we can do that best. And that takes me to the end of my introduction, and Stephen is now going to present the second half.
Thanks, John, and once again, apologies on behalf of James Lockman. He really is disappointed not to be here to present this work. So I'm going to do this. I'm going to go over in a little bit more detail the visual performance-related issues and how macular pigment, it's no longer a hypothesis that macular pigment is necessary for optimal visual performance. It's absolutely not a hypothesis. That is now an optical fact. That is a fact. And the reason it is twofold. Number one, it contributes to the speed of visual processing. And two, it acts as an optical filter. In order to really understand what we did and why we did it, we're going to have to go over some very basics of vision. It's really for the people who don't know anything about vision, so I'm thinking about the chemists and the ophthalmologists in the audience. So this is very simple. This person has macular pigment, and the blue light doesn't get through as much as it would otherwise. And it's not just a little bit of blue light it filters out. It blocks out 40 or 50% of the incident blue light on the macula. So it's a lot. whereas this patient who hasn't been eating any fruit or vegetable has no macular pigment and all the blue light gets in, causing optical aberrations, which you'll understand in a few minutes, but also causing oxidative stress, which isn't really relevant to this talk. Now, we're going to get into some very basic stuff here. When you go to your local optometrist, you look at this. It's called visual acuity chart, Snellen, invented in 1862. And it's a bit like the English language in that it's just become so global and so dominant that it is the language even optometrists and ophthalmologists speak. And all it is with 100% contrast, black letters on a white background, how small a thing can you see? So it's really the resolving power of the eye. Okay? Contrast sensitivity, on the other hand, is really how faint an object can you see against its background. And study after study after study has shown that this is a much better indicator of your visual performance and experience than this. But this is so dominant in our culture, because it was introduced clinically and on the high street 100 years before this, that unfortunately this is what we do. And that's what we need to change. For example, every week I do about 12 or 13 cataracts, and they may well have 6/6, 20/20 vision. But their contrast is dramatically reduced. They're complaining of poor vision. I take the cataract out. They're still 6/6, but they're absolutely delighted because their contrast has improved. Now, we need to understand that. And a much better way of explaining this is this photograph here. There's a man, and you're looking at him with normal contrast. Contrast, we use different spatial frequencies. A spatial frequency is a posh word for a target size, okay? So a high spatial frequency is a small target size, and a low spatial frequency is a large target size. So if you only see the high frequencies, this is what you'll see. If you only see the low frequencies, you'll see a blurred image. But if you have full contrast at high and low spatial frequencies, you see it as you should see it. Now that brings us to blue light, and why is blue light relevant to all of this? And we have to concentrate a little bit for this. This bit's a bit sciencey. Blue light is scattered. Light is scattered as it comes through the atmosphere or as it goes through parts of your eye. It's scattered because it hits particles. The amount of scattering is proportional to the inverse fourth of the wavelength. In other words, the shorter the wavelength, the more scattering. And it makes sense. If you have a small particle here and it hits into a small wavelength here and it hits this small particle, it'll be scattered all over the place. Where if it's a big wavelength, it'll go through and not really be bothered. Therefore, of the visible wavelengths, the only wavelengths that are scattered to any meaningful degree are the blue wavelengths. Okay, so you have to remember that for the rest of the talk. Now, when light comes straight into your eye, it's scattered, only the blue part. And if it's axial and it's very strong and so intense, it causes dazzle, also known as photostress, also known as glare discomfort. And it blinds you, and it's a very common cause of road traffic accidents. And the Hammond group have shown, A, that it's the blue wavelengths. So the threshold for causing that intolerable glare and blinding you for 5 seconds is much lower for blue light. B, the lower the macular pigment you have, the worse your recovery from that dazzle. And C, if you augment your macular pigment, your recovery time improves. And that's very important from a safety perspective. And we're going to call that glare discomfort, not to be confused with glare disability. Glare disability is when your eye isn't adapted for the illumination, that light scattering affects contrast sensitivity, which we've already defined, which you now understand. Okay? So it really relates more to light coming in from the side, but it's not so bad that it dazzles you, and you can have glare disability at nighttime or daytime. It's easier to give you an analogy at nighttime. If you hear some rustling in the bushes at the back of your garden, and you think it's a burglar, and you're looking at it, and you can see the bushes quite well, and but you have a headlight or a floodlight in your back garden. It comes on towards you, not so much that it dazzles you, but enough that you're not ready for it. And suddenly behind the light, you don't see any bushes. It's all black. That's glare disability at nighttime, and it's worse at nighttime. Again, it is the blue wavelengths which are scattered, and the Hammond lab have shown that glare disability is worse if you have low macular pigment, and that glare disability improves, so your visual performance under conditions of glare improves with macular pigment augmentation. So most things I've spoken about now are internal to the eye. Now we're going to talk about light scatter outside the eye. So I've mentioned that it's still the only wavelengths that are scattered are the short wavelengths of light. So when sunlight comes into the atmosphere and it hits the terpenes, the ozone layer, only the blue light is scattered. And when you look at distant mountains, what you see is the distant mountains are a blue haze. And although it looks nice, you can't really discern the foliage as if it was closer. In other words, your visibility is reduced. And that is because the blue light is scattered and it causes what's called a veiling luminance. And the best way to explain this is if I give you a weight, I put a blindfold on you and I give you a weight of 1 kilogram and I ask you to lift it. And then I give you a 2 kilogram weight. You can tell which is heavier. That's because, but if I give you a weight of 1 kilogram and then a weight of 1.1 kilogram, you can't tell the difference with the blindfold on. Okay? That's because the just noticeable difference for lifting weights is 0.5 kilograms. Now, for contrast sensitivity, to see one thing from the other, the foreground from the background, the just noticeable difference has to be 1/60th. So something has to be 1/60th brighter or 1/60th dimmer for you to see it. But with veiling luminance, the light, the blue light, is scattered. And it increases the luminance all over your retina. It veils your retina with luminance. So now, everything's lifted. So the just noticeable difference is no longer 1/60th brighter or 1/60th dimmer, but 1/30th brighter or 1/30th dimmer. And the best way to explain this is the barbecue analogy that Graham O'Regan came up with. You're at a barbecue on a Saturday afternoon, and you're cooking your burgers, and you look at the embers on the barbecue, and they're all grey. You can't see one from the other. 3 hours later, same barbecue, same embers, same luminance, but no veiling luminance, and you can see the embers one from the other perfectly well. Okay, so these are the mechanisms. There's one more optical mechanism whereby contrast sensitivity is enhanced by filtration of blue light. And that is, if you have two leaves which are the same luminance, but slightly different color, slightly different green, and you put a filter over it, macular pigment is a filter, if you put a filter over it, it will filter one wavelength more than the other, and it increases the contrast in spite of equal or near equal luminance. And that's called chromatic contrast. And again, the Hammond lab has shown that that is also directly related to macular pigment in such a way that you can enhance your contrast in a way that is proportionate to the differential absorption of the two colors in question by that filter. So that's pretty much everything you need to know about light filtration, blue light filtration, and how it's important for central visual optimization other than visual processing. And visual processing is, it appears that lutein and zeaxanthin and mesozeaxanthin are also important for gap junction, interneuronal communication. And it has been shown that visiomotor function, that's the speed at which you react, is also related to macular pigment. So long story short, it's no longer a hypothesis. It's a fact that macular pigment is important for optimal visual performance. And from a Darwinian perspective, that makes sense. We're not going to evolve to develop a pigment which protects us from age-related macular degeneration. Serendipitously, it does, because it filters blue light and it's antioxidant. But it's there to give us a visual advantage over our competitors. Now, about the trial. So what we did was, it was a placebo-controlled trial. So small, 12 subjects in each group. So they either got placebo or MacuShield, MacuHealth, which is a 10-10-2 formula, 10 milligrams of mesozeaxanthin, 10 milligrams of lutein, and 2 milligrams of zeaxanthin, or high lutein with 20 milligrams of lutein and 2 milligrams of zeaxanthin. We measured pretty much every test. That included macular pigment at every eccentricity that can be measured with our equipment, best corrected visual acuity, contrast sensitivity, glare disability, photostress recovery, ocular stray light, and visual discomfort rating. We're going to show you the positive findings. We don't have all of the slides because James didn't get them to us. So long story short, with the 10-10-2 MacuHealth, MacuShield formulation, the rise was higher and greater compared with the ultralutein, and the baselines, in terms of baseline variables, the three groups were statistically comparable, and the placebo did not increase their macular pigment. And you will also see that in group 1, there was only an increase in macular pigment at one eccentricity. That is the ultralutein. Now, we're now looking at contrast sensitivity under mesopic conditions. There was only, with the high lutein, there was only one spatial frequency, one target size that made a difference. With the MacuShield, MacuHealth formulation, every spatial frequency improved, whereas with placebo, there was no improvement. That was an outlier, which didn't affect the statistics. Now, we don't have James's slide for photopic, but just long story short, with group 2, that's the MacuHealth, MacuShield, there was an improvement with photopic contrast sensitivity at 3, 12, and 18 cycles per degree. So that's 3 target sizes, but not at any spatial frequency for either the placebo group or the ultralutein group. We're now going to look at contrast sensitivity under glare disability conditions. This is photopic. And what it shows is that with the 10-10-2 formula, there was significant improvements at these 3 spatial frequencies. They're large target sizes, but not at these 2. At only one spatial frequency, at no spatial frequency for the ultralutein or for the placebo group. When we look at mesopic contrast sensitivity under glare, we don't have the slide of that. Group 2, again, the MacuShield, MacuHealth, showed improvements at all spatial frequencies except the largest, 18 cycles per degree. And group 1, that's the ultralutein, this is for mesopic contrast sensitivity under glare, showed an improvement only at one spatial frequency. And this has been published in IOVS, and there are copies of the paper downstairs if you need it. So long story short, it appears there is a consensus, unanimous in this room, that macular pigment is important for optimal visual performance. Our study does indicate that a 10-10-2 formula of mesozeaxanthin, zeaxanthin, and lutein does offer visual advantages over the other in this small study. The weakness of this study is the small numbers, and that will be addressed by this grant, which we've just received from the European Research Council, which will, in essence, be measuring macular pigment in people with low macular pigment to start with, but completely healthy eyes, and comparing a placebo with the 10-10-2 formula. Thank you very much.
Thank you very much. We have time for some questions.
One of the things which came up in the study was, in fact, there was an improvement in contrast sensitivity, although between 3 and 6 months. Although, in fact, the macular pigment did not increase. If you remember on the slide, it went up at 3 months.
Yeah, that's right.
It plateaued off with the MacuShield.
And when we submitted,
what was interesting was that it still continued to increase contrast sensitivity. And it's on that basis we think it was affecting the brain as well as the actual eye itself. Would you like to comment on that?
Yeah, that's exactly right. We were asked by the reviewers of the paper to speculate on why the contrast sensitivity improved before the macular pigments increased significantly. And either it had increased, but not significantly, but maybe it was clinically meaningful in spite of not being statistically significant. Or B, that it wasn't entirely optical, and maybe it was neural processing that was involved. But we're speculating at this stage.
So So I've been hearing over the past couple of days this notion of a clinically desirable spatial profile for macular pigment. And I wondered if you could comment on that, because one thing that it's one thing to say that more people have an exponential distribution than sort of a central dip. I mean, in the US, there are more obese people than not, but it's not clinically desirable just because more people have it. So I'm sort of curious to know what you mean by clinically desirable and what the evidence is that a central dip or anything like that is necessarily a bad thing.
Well, first, the term was never used clinically desirable. Desirable was used.
It was used on the optometry day.
Yeah, okay, but I've never used the term and clinically desirable. But anyway, that is based on a large study we did, which looked at, amongst 828 subjects, those who did have macular pigment dips compared with those who did not. And it was 828 normal people, and what we found that risk factors for age-related macular degeneration, which included increasing age and smoking, were associated with a very significantly increased risk of having this dip. And it is on that basis that we say it.